In problem number 10, we're given the second derivative of a function. It's been already calculated for us, and it has even been factored out. And the question in the problem is asking how many inflection points does the function f of x have? Not the function, not the second derivative of f of x, but the original function f of x, which is not even given to us. How many inflection points does that function f of x have? The process of finding inflection points is very similar to the process of finding relative maxima and relative minima, except that when we're finding relative maxima and minima, we're working with the first derivative of the function. But when we're finding inflection points, we're working with the second derivative, but the process is almost the same. First of all, it might be a good place to remind you what inflection point is. An inflection point is a point from where the concavity of the function changes. Concavity refers to the way the graph of the function bends, and there are two ways in which this can be happening. The graph of the function may look like this. This shape is concave up, and we can recognize that the graph has a shape like that by looking at the second derivative of the function, and if the second derivative of the function is positive, then the function is concave up and the graph of the function will have this shape. Now the concave down shape looks like this. And the function is concave down when its second derivative is negative. A good way to remember which is to remember that the concave up graph resembles that of a parabola that opens upward, and the concave down graph resembles a parabola that opens downward. In fact, y equals to x squared is the typical example of a function that is concave up, and the function y equals to negative x squared is a typical example of a function that is concave down. Now, an inflection point is a point where the shape of the graph changes from being concave up to concave down. So, for instance, the function may be concave up, and then at some point right here it may change the way it bends and bend the other way. And so this point that I marked on the graph here is an inflection point. In this example, prior to reaching this inflection point, the graph is concave up, so we can say that the second derivative of the function is positive. After passing through the inflection point, the graph begins to bend the other way, and the graph is concave down, so the second derivative of the function will be negative. And so we observe that at an inflection point, the second derivative changes sign from positive to negative, and it can also happen the other way around, from negative to positive. But one of the consequences of this is that at the inflection point itself, the derivative should be equal to 0. F double prime of x, the second derivative of f at an inflection point x, must be 0. Now, one has to be a little bit careful, because just like not every critical point is necessarily a relative maximum or relative minimum. In order for a critical point where the first derivative is 0 to be a relative maximum or a relative minimum, there has to be a sign change for the first derivative at that point. The first derivative should either change from positive values to negative, or the other way around. And something very similar takes place here with inflection points and second derivative. If you found a point where the second derivative is 0, you cannot automatically assume that that point is an inflection point. In addition to the second derivative being 0 at a point, in order for that point to be an inflection point, which should happen in addition to the second derivative being 0, there should be a sign change of the second derivative at that point. For example, the second derivative may change from positive values to negative values, or vice versa, and that's when the such a point will be an inflection point. But when we're looking for an inflection point, the first step is to calculate the second derivative, set it equal to 0, and solve for x. Now, in this problem, we are already given the formula for the second derivative, so what we will do is we will just set it equal to 0 and determine the values of x for which that happens. Now, since the derivative here is factored out, it's very easy to determine the solutions. In fact, you just set each of the factors equal to 0 and solve for x, and that gives us our critical point, points where the second derivative equals to 0. The first of these points is x equals to 1, then we have x equals to -3, and then we have x equals to +2. Now, what we need to do next is we need to look at the signs of the second derivative on intervals in between these points. So let's go ahead and draw the number line. We will mark these points on the number line, and then we will determine the signs of the second derivative on those intervals. I need to copy this formula for the second derivative. Okay. So f double prime of x equals 5 times x minus 1 squared, and then we have x plus 3 times x minus 2. And so I'm going to draw the number line, x-axis, and I will mark the points where the second derivative is equal to 0 on this number line. So one such point is -3. Another point is 1. And then another point is 2. So we have 3 such points, and these three points divide the number line into 4 segments. The second derivative is equal to 0 at those 3 points, and everywhere else it's not equal to 0, so it's either positive or negative. And now we just need to determine where exactly it's positive and where exactly it's negative. Just like we did for intervals of increase and decrease using the first derivative, we will accomplish this by selecting test points. For example, in the first segment, we can select a test point of -4. Between -3 and 1, a convenient test point to use is 0. It really doesn't matter which test point you use, but it's always almost always a good idea to use 0 because it's easier to calculate with 0. In between 1 and 2 we can select 1.5, and then on the last interval we can take 3 or 4 or 5. Let me take 5 for example. Okay, so now we simply plug in these test points into our second derivative, and we do not need to know the exact value of the second derivative at these test points. We just need to know whether those values are positive or negative. Okay, so for instance, if I plug in x equals to -4 into the second derivative, we will get 5 times -4 minus 1 times -4 plus 3 times -4 minus 2, and so that's positive times another positive, because -5 squared is positive. Then we have a negative, and now we have another negative. And so a product of 2 positives and 2 negatives is going to be a positive result. And we conclude that the value of the second derivative at -4 is positive. And so we'll put a plus sign for the first segment. This is a sign diagram for the second derivative of our function. And basically what this is telling us is that the function f of x is concave up on the first interval. Repeat this process for the other test points. You will find, I will skip the calculations and will just tell you the results, and please confirm that. So if you substitute 0 into the second derivative, the outcome will be negative, and the function will be concave down on the second interval. Then at 1.5 we will have again a negative result. So again the function will be concave down on the third interval. Finally, at x equals to 5, we're going to get a positive value for the second derivative, and the function will be concave up again. So now if you examine what happens at the 3 points that we identified where the second derivative is equal to 0, we see that as x changes and goes through the point -3, we have a sign change, right? So imagine that x crosses this point -3, moving along the x-axis. Then we will observe that the second derivative will change values from positive to negative, and there is a sign change in the second derivative at that point. Therefore, this point -3 is an inflection point. Now, unlike this point -3, at the point x equals to 1, even though the second derivative is 0 at that point, we do not have a sign change in the second derivative at that point. The second derivative is negative to the left of that point, and it is also negative to the right of that point, so that point is not an inflection point. And then finally, at x equals to 2, again we have a sign change from negative to positive for the second derivative, therefore 2 is an inflection point. So out of these 3 points where we have a second derivative taking the value 0, 2 of those points are inflection points, and the third one is not. Overall, our function has 2 inflection points.